All right. So the last time we met, we looked at just what are equations. And an equation is a sentence. It is a declarative sentence. It tells you what happens. Basically, can you put your bit down, please? It says these things become those things. And this is, again, pretty astounding. We've only been able to do this for a couple hundred years with any sort of accuracy. Beforehand, there was a lot of secrets and codes and that sort of thing that the alchemists had, and they were changing one thing to another, but they really had no idea what they were doing. But gradually, things came together, facts got a little clearer, and Lavoisier was able to compile those all and give new names that we continue to use today. And you know, other people, of course, were involved as well. But he's the one that really got it over the hump to a standard worldwide way of speaking about how things change. And again, for most people, they don't walk around saying, "I wonder what this is made of," and "I wonder what it would change into if I burned it." Or, you know, normal people don't do that. But we have so many advances because people did think weird things like that. If I mix these two things, what'll happen? If I add this thing to that thing, what'll happen? What effect will that have on my body? What will it do for food? You know, all those things. What sort of weapon can I make out of it? To be honest, a lot of people think that way. But you know, for every weapon that's been come up with, there have been 5 or 10 good beneficial things that have really affected our lives. And until you're aware of that, then it's just trivia. But it's not trivia. The more you learn about this sort of thing, it becomes more and more just a real blessing you live today and not 200 years ago. All right. Well, now just writing those word equations, and there's an example, or simple equations, isn't going to be enough because it doesn't tell the whole truth. Excuse me. It doesn't tell the whole truth because we don't want to just say what becomes what. We want to say how much of what becomes how much of the other. Okay, how much of A becomes how much of B. Not just does A become B, but how much. Because again, it's very wasteful to expect a lot of something and use a lot, but then you actually only get a little bit. So you want to be able to predict and make the most efficient, not just effective, but the most efficient use of your resources. Earth is finite, and if we make a lot of waste or we use up too many resources, then, you know, game over. So we have to balance them. What that means is we need to be able to say how much of each thing is predicted, and we need to do it accurately. So think about the metaphor of a bicycle. Okay, think about trying to build a bicycle. You have a bunch of parts, and you want to build a bicycle together. Okay, you got to have a frame, you got to have wheels. How many wheels do you have on a bicycle? Okay, good. 2 people are listening. All right, good. Yes, 2. Right. The bicycle has 2 tires. You've got to have pedals. How many pedals? All right. How many handlebars?
1.
Depends how you define handlebar, right?
Yeah.
All right. 1 bar, 2 handles, so handlebar. Yeah. And that gets you 1 bicycle. So we have these reactants or reagents, and then we have a product. Of course, you could double it and get 2 bicycles, triple it and get 3 bicycles, so on and so forth. But first, you have to think about what it is and put it out in plain English. Then you want to symbolize it, but we don't have symbols for, you know, pedal on the periodic table. You need to be able to order the right amount, not too much of one and too little of another. So if we did use these symbols here, F for frame, not fluorine, but frame, W for wheel, not tungsten, but wheel, H for handlebar, not hydrogen, and P for pedal, not phosphorus, then we could get the frame, 2 wheels, 1 handlebar, and 2 pedals. Again, you could say, well, but the pedal is connected to each other, and the gear, nobody mentioned the gear. Okay, there's more we could do with this, you know, if we wanted to, because obviously without the chain, then the bike isn't going to do you much good. Well, I take that back because My 3-year-old really enjoys his balance bike, and it has no pedals or chain. So it's still, is it really a bicycle? That's debatable. Anyway, so that would be the formula. Say again? Oh, sorry. Oh, okay. So this would be the formula based on the parts we identified: the frame, the wheels, the handlebar, and the pedals. Okay? So we got to say how many things we need. And so we need to put big twos in front of the wheels. Okay? Because one is wrong. If you just have one pedal, yeah, you can have a downstroke, but how are you going to get that pedal back up again without the other to push down? Okay? You can't pull up on a pedal. And again, yes, there are bikes where you can have your toes in the little socket. I don't like those. They always make me afraid I'm going to crash and break my ankle or something. Anyway, so you use the downstroke of one to bring the other one back up. Down, 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 down. Never pull, 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 pull. Same thing with wheel. Yes, you can have a unicycle, but that's not what we're building. We're building a bicycle. All right, so once we put those numbers in front, okay, so the whole thing, we have two of it, then we can get these little numbers in subscripts in the product. That inside this one bicycle, we've got a couple wheels. Inside this one bicycle, we've got a couple of pedals. Inside this one bicycle, we've got one handlebar, and inside this one bicycle, we have one frame. So these numbers in front are called coefficients. The little ones down to the right are called subscripts. Sub for under, script for writing, so writing under. And so these are coefficients. You've done this in algebra class. These are constants. The symbols would be more like the variables, all right? And again, you are adding these together and getting one new thing. Yes, in math class, if you just put variables next to each other, that implies you're multiplying. It does not imply that in chemistry. Okay, that means they're added together, all together in one molecule, one substance anyway. Okay, so coefficients. Everybody say coefficient. All right, good, good, good. So if you have the right number of atoms, you can double check it. Again, 2, 2, 1, 1, so on and so forth. Okay, we have to conserve mass. One of my biggest things that makes me cringe as a scientist, or at least a science teacher, is when I watch a cartoon, and I watch cartoon science. Okay, when I watch things get created out of nowhere, that hurts my chemistry heart. When I see things changing direction in midair without any wings or rockets, that makes my physics side hurt. When I see characters get slammed by things and just walk away, maybe with some stars or birdies, that hurts the biology side of me. Like, they should be dead, right? How many cartoons everybody should have died the first episode if they were in real life? All right. Okay. That would traumatize kids, though. And so we teach kids that nothing matters and you can do anything you want. Exactly. That's one of the classics, yes. If you don't know about it, it doesn't apply to you. Okay? But in real life, it does. Say again? Oh, yeah. Animals aren't usually scared of you. All right. Yeah. They're there to eat the mosquitoes that would like to eat you. So it's a trade-off, right? All of them, yes, yes. Just have humans and pets, yes. That would be ideal. That'd be ideal. But we have to conserve mass. This is like rule number 1, literally, in chemistry. The same thing at the end that you had at the beginning. And yes, we kind of threw that out with the nuclear chemistry chapter, but that's the one exception. Everything else, anytime you change the identity of something, you have as much left. Now, some of it may have gone up in smoke, but it's still out there somewhere. It's just gotten diffused into the atmosphere. And if you do it inside a sealed container, if you burn something inside a sealed container, it's all still there. The exact same number of carbon atoms, exact same number of oxygens that you had to begin with. All right. So as you convert them into products, you break bonds and make new bonds. Okay? This is very, very important. It takes energy. to break a bond, to push atoms away from each other. They like being near each other, okay? They like being near each other. It takes energy to push them away from each other. But then when you make new bonds, then maybe they like their new partner even more. And so that will release even more energy oftentimes than what they had to begin with. Not always, but oftentimes. Now, you can't actually create or destroy atoms. They're just rearranged, and you conserve the mass, as I said. So you write the skeleton equation as we were doing last week, and you make sure you have the same kinds of elements, and then make sure that you look at the numbers. You are not allowed to change subscripts. You are not allowed to change subscripts. Let me say it one more time. You're not allowed to change subscripts, okay? But you may change coefficients to your heart's content until it's right. Change coefficients to your heart's content until it's right. So for instance, we have a carbon, we have an oxygen molecule, and we end up making carbon dioxide. Very, very common. This is just called burning coal. Okay, burning coal makes carbon dioxide if you do it right. Of course, if there's sulfur or something in the coal, then it'll also make sulfur dioxide, and then that's a problem. But just to begin with, here is one where the coefficients are all 1, and it's actually correct. 1 carbon, 1 carbon. 2 oxygens, 2 oxygens, right? And again, looking at the symbols, which is what you normally would do, 1, 1C, 1C, 2 O's, 2 O's. Okay, yay. If there's no coefficient, it's 1, okay? Just like if there's no subscript, it's 1. On the other hand, though, when you make water, then you're burning hydrogen, and that's all water is burned hydrogen. You don't quite get the right numbers. You have 2 H's, okay? You have 2 O's and 1 O. Wait, where did the other O go? Uh-oh. So you're gonna have to make 2 waters. Okay, you got now we're okay. We got 2 H's. Sorry, 2 O's. Oh, but wait a minute. And now we got 4 H's. And I'm not talking about farming. Oh, well, I got to put another 2 out there somewhere. Where should I put it? I put a 2 in front of the water. Where? Say again? All right, let's see. All right, I'm going to have to double the hydrogens, but I don't want to double the oxygen. I don't want to double the number of oxygen molecules, but I will double the number of hydrogen molecules. All right, so again, 2 hydrogen molecules makes 4 atoms. 2 water molecules makes 4 hydrogen atoms. Check. 1 oxygen molecule makes 2 oxygen atoms. 2 water molecules makes 2 oxygen atoms. Check, check, check. So, all right, I've got to put the 2's in both places, and it's now balanced. Yay. So we can use fuel cells, just burning hydrogen, and all that comes out of the exhaust is steam. That's it. It releases a lot of energy. But why is it that we might not, why aren't all cars running on hydrogen right now? It's so effective and so clean. Does anybody know somebody who, you probably know people who drive electric cars, but do you know anybody who drives a hydrogen fuel cell car? They exist. You can buy them if you have money. Why are they expensive? Why are they rare? Okay, so it's very rare. So rare you hadn't heard of it. All right, what else? Imagine, what is it hard to get the oxygen? No. Is it hard to get a spark to burn them? No. The hard thing is getting the hydrogen, okay? Because, darn it, hydrogen likes to blow up. Remember the Hindenburg? Okay, so you gotta be able to get it really easily. Easier than putting gasoline in your car every couple of weeks, or more often, depending on what it is. But you gotta make it so that idiots out there don't blow up their cars the way that they do when they carry gasoline around in plastic bags, sometimes. Say again? Yeah, a couple of weeks ago, there was this fuel shortage because of pipeline. Anyway, yeah. Yeah, exactly. And so some people, they didn't have enough of those like gallon gas containers. So they were hoarding the gas. Anyway, some people were filling up like wash basins, just open top things like yeah. But a couple of them, as they were driving home, it ignited into flames and burned their cars. Yeah,
Wait, if you
it's their own fault. Exactly.
if you driving around with gas, if you go,
Absolutely.
yeah,
Yep. Yeah, that's why you're not allowed to smoke at the gas station. All right. Say again. No, if it's in your gas tank, it's fine.
No, I'm saying like if it's in a bucket, like
A bucket, yeah, that's it. If there's any spark, then the fumes can go up in flames, and then the whole bucket will go up because it evaporates very easily. Yeah, it's fine. I don't mean it's fine to smoke in your car. Don't get me wrong. But the gasoline that you put into your tank is completely separate from the whole rest of the cars. It's very, very safe. Maybe your first cars from 100 years ago weren't so safe, but now they are. But if you have, what do you call it? If you have a like for your lawnmower or whatever, you have a gallon filled with you got to make sure it's capped, and they have these really annoying safety caps on them now to make sure no fumes get out. You can still smell it, but that's much safer. But some people just carry it like in a bucket, like what happened then. And then yes, the slightest. I mean, just even like turning on your turn signal as a little spark in the steering column. It never means anything usually, but it could, Or you push in the little cigarette lighter or something again. Just a little spark of electricity. Normally, completely wouldn't even notice. Charging your phone. I don't know, and then up you go. So don't carry gasoline open. Anyway, fuel cells. They are working on making it idiot-proof, but they're not there yet because people are dumb. All right, I say that as a person. All right, so that's a really, really long summary of what I just said. You're going to know that by doing it. Okay, so balancing a chemical equation, students suspended copper wire in aqueous solution of silver nitrate. So again, you've got to interpret what this is. So silver nitrate, okay, we learned those polyatomic ions. 8 is great. It's going to have nitrogen, and 8 means element 8. It's going to have a lot of oxygens, and lo and behold, there's nitrate down there. And you might not remember that it's a 3, but it's going to have nitrogen and oxygen. And it's silver, so it's Ag, and it's aqueous. And you had copper wire, so it's pure copper. All right. Well, they noticed a deposit of silver crystals on the copper wire when the copper reacted with the silver nitrate. They recorded the reaction for the equation, but they didn't balance it. So now we need to balance their equation. So again, here we start with silver nitrate and copper, and we end up with copper nitrate and silver. So what do we do first? Well, first, of course, we have to make it into this simple equation, but that was last time. Now what do we do? Gavin, any idea what we do now? No? All right, so there's a certain order that you should look for balances. When you're doing it, where did that? Get it later. Oh, there it is. All right. When you're trying to balance things, a couple of rules. Always balance oxygen last. Okay, oxygen's in so many things. If you try to balance with it first, you're going to have a problem. So what you're going to want to do is you want to go from positive to negative. It's just a rule of thumb. It's not absolutely necessary, but it keeps things orderly. So start off with metals. So you want to go from positive to negative when you're balancing. You want to start off with metals. So what have I got here? I've got Ag, and I've got Cu, copper, right? Silver and copper. And this is called an RP chart, reactants and products. You've got silver, copper, reactants and products. And just initially, I look and I see that there's one of every other. There's one silver in the reactants, and there's 1 in the products. So that's good. There's 1 copper in the reactants and 1 copper in the products. All right, that's good. Now I've got something else in here. All right. All right. I got anions. In this case, it's NO3 minus, but I don't really care about the charge right now. It is very important that you do not break up polyatomic anions. Just treat them as one thing. NO3 is one thing. Okay, NO3 is one thing. Hi, Tosh. 844. Okay. NO3 is one thing. It's not an N and 3 O's. It is one thing. Everybody got that? Nitrate is one thing. All right. So I start off with 1, but darn it, I end up with 2. I was so close. 5 out of my 6 numbers were 1, but nitrate had to ruin it on the right. So now I got to figure out what to do in order to make these numbers right. So first thing I want to do is when there's a disagreement, I've got to up 1. Okay? So I've got to not make that 1, but 2. But if I do that, I cannot change the subscripts. So what goes along with the nitrate on the left, on the reactant side? What's attached to the nitrate on the reactant side on the left? Austin? What's attached to the nitrate on the reactant side of the equation? Yeah. All right, Ag, right, exactly, Ag. So when I double this nitrate on the left, I am obliged to double the silver on the left. Okay, so again, I doubled the nitrate on the left, I have to double the silver. They go together because I put a coefficient in front, and you'll see this on the next succeeding slides. But now, my silvers aren't balanced. So then, I've got to balance them. Now, if I double the silver on the right, then I don't have anything attached to the silver. So I can say I'm done. I've got 2 silvers, 1 copper, and 2 nitrates all along the way. All my numbers are equal, 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 equal. Everybody see that? RP charts are your friends for balancing these things. Go from positive to negative, top to bottom, positive to negative. Know your anions, polyatomic anions, and I guess ammonium for a cation, but know those so that you can not accidentally break them up, because I did that when I was a student, broke them up. All right, so let's see what they say. All right, we have nitrate that is a product and a reactant, so just use it as a unit. Then, in order to balance it, you put a 2 in front of AgNO3. Again, you cannot change the subscript, but you can't put a 2 there. Well, if I've got 2 there, then I've got to have 2 over here, and then I've done it. I'm going to stop there for today because I think that's a good place to stop. And I'm just going to stop the recording now.